Know that homework was due, but I posted a couple of videos to review polar coordinates. Has anybody done that? So it's just gonna be easier to follow. We are switching our geometry. So we used to have two parallel slits, literally, in between these two papers, right? And that calls for Cartesian coordinate system. One thing that is really nice about Cartesian coordinate system is when I draw the coordinate system, I have those three orthogonal lines. They're the same everywhere you move around. And my entire system is broken into boxes, and all those boxes, if I think about them as unit boxes, like unit in X, Y, Z, all of them are the same, cubes of the same size, wherever I move around. If I have something like this, which is cylindrical geometry, this is a piece of tubing, and this is a piece of tubing from our labs. Any kind of equipment that is manufactured is typically in this shape. Our bell bores are in this shape. I mean, everything, a lot of manufactured things come in this shape. Now, if I'm forming my balances, I have to orient my system parallel to these solid surfaces. But the way it makes sense to describe this, and this is also an orthogonal coordinate system, is with radial coordinates. So basically from this point, I have this side is in the constant radial distance from a center. So I'll put one of the axes, which is going to be my z-axis, in the middle of this, right? And then I describe wherever it is that I can put starting sort of point for my r is always like at a constant distance from it. That's my radial distance. And I just need also which direction I'm going. And that I'm going to describe with a theta, which is an angle, whether you want to use angle in radians or in degrees, doesn't really matter, as long as you know what you're taking cosine or sine of. And you just place a line where you're starting from, and then you have theta from that point, right? So then every point can be described by radius, by theta direction, then radius how far away from the center. So direction, center, the distance from the center, and also how much up or down, that remains z. This is still an orthogonal coordinate system. However, what's interesting is that it's curved, surfaces are curved. And now my plane of, so normally I have in Cartesian coordinate systems, I have those x, y, z planes. There are planes where my x, y, z is constant. My plane where my radius is constant is curved, which is what I want. But I'm constantly changing direction as I'm going around that plane, going in a circle, right? Imagine that direction is technically, so direction of the change of actually theta along that surface of constant r is constantly changing direction. So at every point, I can still place an orthogonal coordinate system. There will be a z in our standard z direction. There will be r, which will constantly change direction, where is this r vector pointing. And there will be theta orthogonal to r. Okay? So basically I go, and that theta direction also changes and moves orthogonally around this. Right? As I move out, okay, like, so look at this shell. This is a shell between r and r plus delta r, like small delta r. Yes? This shell that I'm looking at. It's curved, and its inner surface here is different from the outer surface. When I had a little cube, that wasn't the case. There's delta x times delta y wherever you go, right? Now this surface is growing as you're moving up. Okay. And that causes problems in forming. So suddenly my relationships between gradients and surfaces and areas become a little more difficult. This is why when you integrate in cylindrical coordinate system, that area element dA is suddenly r dr d theta. It's not just dx dy. Because you have to, it changes with r. At a different r, it's larger. And you have to account for that. And that r dr d theta, that r accounts for that. Right? So suddenly my double integrals become a little more difficult. So I basically now, in a nutshell, describe those two videos. Watch them for a good review. There's a video and there's a link for basically how do you do double integration. Why is that important? I'm ultimately, when I'm flowing through this, what I measure as an engineer, I take a cut, as an engineer, I take a cut and I measure flux through this. So there's certain volume coming through. I gotta integrate, if I have a velocity field, over this entire area, which is now in polar coordinates. So my integral has to be integral r dr d theta, right? So for all the things. So essentially, it's from 0 to r, some sort of radial distance, depending on my tubing. So you need to know how to do double integration in cylindrical coordinate system. So we're going to now do the same thing that we did for our Cartesian coordinate system. It's just that we're going to balance over a curved shell like this in a cylindrical coordinate system. That's essentially going to be solving for a flow. We're going to stick to steady state laminar flow of a Newtonian fluid with constant density. That is sort of a mouthful, but we will always be with steady state, right? For now, Newtonian fluids. Not that we're not interested in non-Newtonian, but we're going to go step by step. And constant density for the most part. Right? And what I'm going to change on you is geometry and the boundary conditions. And that will basically change the resulting equations that you actually apply. Okay? But the concepts actually remain the same. So I'm going to, oops. And I'm going to upload, whoop, not this one. Upload these. So I did post these reviews in the slides. But just before we actually go, well, actually, no, I'm going to move on with this problem and then I'm going to get back to boundary conditions. So this is going to be steady state flow of a Newtonian fluid of constant density. And I also will say laminar. And now I'm just going to change. So this is what we already had. That was our thin film, was actually steady state laminar flow of a Newtonian fluid of constant density. We had it down an incline. You're going to, in your homework that is going to be assigned today, solve for the flow in a thin slit, okay, or through a slit. And now what I'm going to do is solve this in a vertical. I'm going to place the tube vertically, in a vertical tube. Okay. So what we have changed here is this vertical tube part, right? And that requires cylindrical geometries. So let me switch to my drawing. Once connected, this computer is not communicating well with this projector, which is a common problem. Resume slideshow. How about this? Save. I'll reopen. Okay. Let's reopen. There we go. Okay. So I have a vertical too. And length L. I have gravity actually down. And there is some pressure difference. Whoops. P0 and PL. Okay. PL. That is driving this flow. If nothing, there's a hydrostatic pressure difference, right, that will drive this. And I have now a cylindrical coordinate system, so I'm going to basically place it here in the middle, and my Z will point downwards. It's a matter of choice. And my R will point in this direction. And technically, if I was showing my theta coordinate vector, it would be on a circle here. This is my theta direction, right? That changes around the tube. So I still have three coordinates. So R, theta, and Z are my coordinates. So I know that I can switch, actually. I have a coordinate mapping. I have functions that take me from x, y, z coordinates to r, theta, z, right? Z remains the same, z, z, z. And I know that my x will typically be r cosine theta. My y is r sine theta. And z is z, if you will, right? So this is how I go back and forth. Now my shell over which I'm balancing things, so what used to be from x plus delta x, and we had z to z plus delta z, we had a little rectangle, right? That rectangle now, for this flow, I'm going to assume that my velocity is a vector. Velocity is what is. Question is, what are the coordinates that I'm going to describe it in, right? So that vector will be expressed with different coordinates depending on the coordinate system I pick. So my velocity is velocity, but I could look at it as Vx, Vy, Vz. But I could also look at it as Vr, V theta, Vz. Vz is the same in these cases as long as I have the same starting point for the coordinate systems. Okay? Again, velocity remains the velocity. Question is how I'm going to describe it. So now we're going to actually choose this coordinate system. Now, if I'm applying pressure to drive something through a tube, and my solids are safe all around, and I have nothing coming in through the solids or contact with the fluid other than the solid, right? Then I can assume that basically as I'm going in my theta direction, nothing will really change. What will really change is how far I am from the solid surface. That's basically what shapes my flow. My solid surface, if you remember, we have a boundary condition that if this is not moving, my fluid is not moving, or if it's moving, fluid is moving with the same direction. So solid surface imposes this dominant boundary condition. So what is my velocity anywhere else kind of depends how far I am from that solid surface. What coordinate describes how far I am from the solid surface. In the cylindrical coordinate system, which coordinate describes how far I am from this r. So I'm expecting my velocity. If I'm driving the flow, and this is a vertical tube, I'm driving it down, I'm expecting only the velocity that goes down to be non-zero. If I don't have any pressure differences in this plane, nothing should be moving in that plane microscopically. Okay? Only if I perforate here something is actually imposing, right? Then I will have things moving. But right now this is solid, so nothing is driving the flow in any of the cross direction. So now I expect my only velocity that is not zero to be the one going down, which is my z direction, right? And that velocity kind of depends how far I am from the solid surface or from the center, either way. So my vz is a function of r, right? And nothing else. I don't expect any difference, like if I'm here on this side of the wall or this side of the wall, right? So my theta should not make a difference as long as I'm at a constant distance from the center or from the wall, however you want to describe that. Yeah? So essentially, my assumptions are then that my VZ, so this is assumptions, which are very reasonable. VZ is VZ of R, and my other two velocities, V theta and VR, in radial and theta directions, are not there. Okay, so R and V theta are zero. If I start doing stuff, again, I perforate and start imposing some pressure differences that will start driving the flow in the valve or either towards the valve or away, right, depending on what I'm doing, then I'm going to start having radial velocity. Okay, yes?
Like the tube wasn't like had a bigger diameter at the bottom.
Or if I'm changing diameter, yeah, I cannot assume that it's just busy. Okay, then just to kind of adjust to that, I'm going to have some velocities that are also in theta direction. If I start rotating this, viscosimeters, they actually put things in an annulus, and one of them is rotating on the outside. So then I have theta velocity that is only present, right? So it depends what you're doing. How are you moving your equipment? How are you basically engineering it from the outside? In this case, this is static. The only thing I'm imposing is in the z direction, so only vz is non-zero, and the other two should be zero. Make sense? So you do have to think through what it is that you have in the problem. However, our rule for having solvable equations for this course, you have to have one non-zero velocity depending on one other coordinate variable. Okay? Otherwise, you're going to have a little more complex problem and you need numerical solutions. Okay? So this will likely simplify the problem to what we can solve. And then I also see just the way I'm imposing boundary conditions, my pressure should be only function of the z, right? Because I'm imposing one pressure on top, one on bottom. Maybe I'm not imposing anything. I'm just letting gravity rule, right? Gravity rules in z direction. Okay, so basically, I'm assuming P is a function of z as well. Okay. Now I have to put together a shell. Okay? And I'm going to draw pretty much the shell. Should I move this around so you can kind of appreciate? So I'm going to draw a cylindrical shell in this coordinate system. So my shell is described by R to, I'm going from R to R plus delta R. That is the piece of plastic you're looking at. And my Z plus delta Z. And I'm not looking in theta direction because everything is repeated in theta direction, so I'm kind of going to ignoring theta direction this time around. So let's draw that. So I have an outer circle and sort of an inner circle, and this is an exercise in drawing. And even though I have it on my slides, but it's a good exercise to draw. And then I'm going to have sort of, this is my attempt at a three-dimensional draw. This is my delta Z. So I'm going from my plane Z to plane Z plus delta Z, right? And I'm going to change colors. So, and I'm going in this direction. I have R and R plus delta R, right? From here to here. So I have this shell going around. I have only velocity in Z direction, so which momentum am I going to balance first? Right? So we need Z momentum balance. I assumed to begin with that only VZ is there. So this is the first one. In order to basically solve for VZ, you got to balance Z momentum. Now, I'm now in a changed coordinate system, and it seems that only my R and Z are the coordinates that I'm interested in. So I'm not going to have XYZ anymore. I have R theta Z, and theta coordinate, I'm basically, so theta coordinate is ignored. So what is my now selection of my combined momentum? Remember that phi, speaking of the Greek alphabet soup. So phi was my combined momentum. And again, phi, combined momentum, remains phi. Now we're going to express it in cylindrical coordinate system. And we've been kind of talking about Cartesian when defining things. So instead of my phi xx, phi xy, phi xz, I'm going to have r, rz, r, and r theta, but theta I'm going to ignore, right? So technically, we have on this top surface, let's say that I have things that can enter this cup or that shell that I'm moving around. They are orthogonal to this, right? So momentum gets transferred in Z direction. And this is my Z plane. So this is how phi ZZ is going inside. So basically, it's my Z momentum transfer in Z direction. And that phi ZZ, so I have phi ZZ as an actor, that's Z momentum balance transferring across Z plane. And I'm going to also have phi RZ, right? So that's Z momentum transferred across R plane. How does R plane look like? You all have bottles. Where's your R plane? On the bottles you have. Assuming this is actually, it's not perfectly constant, but this is R plane. Okay? It's constant R. So I'm going to have to balance or sum up or integrate or look at the total area that is curved now, right? So this is basically, so this is Z momentum balance, so this is Z momentum transferred across our plane. And this R plane is basically a cylinder surface, right? So my R plane is curved in this system. It's a curved coordinate system. So when I'm looking at things that are balanced around this shell, okay, let me actually I'm going to use slightly different colors for these things. So I'm going to say, and I'm going to draw it in that color, Phi, ZZ. So I have this top surface in my cylinder. So that little shell that I sent around, I have a top slice of it. This is my area now. And I have transfer across from it described by Phi ZZ. Yes? And also on the bottom here, I have stuff coming out also Phi ZZ. But this is my Phi ZZ evaluated at Z plus delta Z. And this is Phi ZZ evaluated at Z. Yes? And then when I'm looking at things entering this shell across R plane, that's this way. Yes? If I was a Velbor producing, stuff is coming in radial direction to my center. Yeah? So that's my, basically, this is my vector phi RZ coming in from the outside. And on the inside, I have the same thing happening in radial direction going out of this shell. So I'm going to draw that, well, I can actually keep this blue color for that. So basically, I have phi RZ acting on this outside surface, and also on the inside, I'm going to draw in a slightly different direction here, phi RZ, right? So this one is acting on the inner surface and on the outer surface, right? So I didn't need that part actually. I have my cup today. So basically, I have phi RZ here on this inner one, and phi RZ on the outer one. So now I gotta balance what's coming in and what's coming out. Okay? And I gotta collect all of the contributions over an area, right? So I'm gonna just call this area up of area AZ, area AZ. I'm just gonna call it AZ for now. And I'm gonna call this area of the constant cylinder here area AR. This outer area of the cylindrical shell. So if I'm balancing what's coming in from the outside, right, I have to multiply by these areas. And what's leaving, I have to also multiply by area. So when I'm doing the shell balance, in minus out plus action of external forces is equal to 0 in steady state, right? That's my balance in words. We're going to basically have, so on top surface, I have ZZ evaluated at Z times area AZ also evaluated at Z. Okay? These areas could change. I'm just going to call it AZ. And what's coming out in Z direction on the bottom surface is phi ZZ evaluated at Z plus delta Z. That's this bottom one. Times, I'm going to call it area Z plus delta Z, which is really, it's the same as AZ, right? the shell. It's better than I'm going to spill stuff from the top. This is literally area of this. Okay? So that's my area AZ. Okay? And this is my area Z plus delta Z. And what can come in through here is orthogonal to it. That's described by PGE. And what can come out of this is orthogonal to it, coming out. And that's described by PGZ, just evaluated at location Z plus delta Z. This is Z, this is Z plus delta Z. Okay? Now, for the other one, I have the RZ is coming in orthogonally to this outside surface. And I have area evaluated at R plus delta R, which is slightly larger than the inner one, AR. Yes? And that's going to create a little bit of difference in the way equations look like. So now I'm going to do in and out across R plane plus phi RZ evaluated. Now I'm going to keep my plus and minus in coordinate system. So I'm going to come in from the inner side, AR, and come out on the outer side, ARZ, evaluated at R plus delta R, and this R plus delta R area. And note that AR plus delta R is larger than AR, right? Which is the difference from Cartesian coordinate system where everything has the same areas. So that's my balance of Z momentum across R. Yes?
So can you explain again the last part? So in what direction is the arrow?
My positive, so here technically I should draw, okay, let me redraw arrows, correct. I was explaining things in terms of the Velbor, so I got carried away. So I'm actually going inwards. Okay. Am I still in blue? Yes. So basically I'm going in and out. And it's positive because here I'm in the area of smaller r, right? Going across. I was producing from the larger r, which is technically in the opposite. Okay, so plus external forces are gravity forces, right? What is the gravity force? mg. And in this case, I'm taking it in, g is the same as its z coordinate, right? And I'm going to do the density, not the mass, because I got to look at the, so basically that's rho g n times the volume. And volume of this cylindrical shell is this area, which is either AC or Z equals delta Z, however you want to describe it, times delta Z. Yes. G and area AZ delta Z, so this is my volume. And all that summed up has to be equal to 0. That's the balance. Now we have to clean it up. One thing that we have to compute is what on earth is this AZ? Right? So I have, now I'm going to do a projection of this shell. So if I'm looking at it from the top, Whoops, I'm messing with my tools. I'm gonna move it. I'm gonna draw it here. So basically my AZ is larger circle area minus smaller circle area, yes? In projection. What is the larger circle area? Delta R squared times B, yeah? And smaller circle area? R squared P. So I'm gonna take P outside. And there is, here it's R squared plus 2R delta R plus delta R squared. Delta R squared is something that is small. So I'm gonna ignore that part. So basically I'm gonna approximate this with 2R delta R times P. So I'm ignoring delta R squared. I'm going to rewrite this because slightly better. Luckily, there will be a video recorded so you can hear me say what it is that I write. So I'm ignoring delta R squared, which is the second order. Okay, so that's my AZ, and it's also the same as AZ plus delta Z. So that is the top surfaces. Now, what is the area of the side? Yes, so it's a perimeter, right? Times the height. So for R, inner surface, it's 2RP is the perimeter times the height. But for radial surface R plus delta R, my perimeter is a little larger. So it's 2 times R plus delta R, P times delta Z. Yes? So basically it's the perimeter of the inner one times, and I kind of cut it and split it open, yes. And it's the perimeter of the outer one. So my AR changes with R. So it's AR is 2RP times delta Z. And my AR plus delta R is 2R plus delta R P delta Z. Okay. So when I actually plug this AZ in here, and AR plus delta R, I recognize that both my VRZ and my AR change with R, right? So I have it here evaluated at R, and here I have to evaluate at R plus delta R. So what I will have is the following. So my phi ZZ evaluated at C times 2PR delta R. That was my area AZ minus evaluated at C plus delta Z, also times that area. plus phi RZ at Z, and now my area AR, okay, and that is 2RP delta Z minus phi RZ evaluated at Z plus delta Z. Oops, it's R. These were at R. To R plus delta R P delta Z plus rho G, and my area A Z to P R delta R times delta Z. Okay, so this was my AZ is equal to 0. So this is the one. So I'm going to shorten this a little with my notation that this is negative phi ZZ evaluated at Z and Z plus delta Z. Do we see this? Times 2 PR delta R. And minus, so this is basically phi RZ. I'm going to single out something, things that depend on delta R. So basically I have this depends on R, and this depends on R. Right? So basically I have RZ times function of R, which is R, both evaluated at R and R plus delta R. So this is kind of radius evaluated at R in radial coordinates evaluated at R plus delta R. Times 2, oops, okay. Two P delta Z and plus rho G 2 P R delta Z is equal to 0. And now I will divide by this volume. So I will divide everything by the volume of the element. And what I'm left here with is phi Z plus delta Z divided by what's left? Delta Z. Minus RZ times R plus delta R divided by R delta R, right? I'm going to write that as 1 over R and delta R and plus rho G is equal to 0. And give me 1 minute to take the limit. So now I'm going to shrink my shell. What I'm shrinking is delta R and delta Z. what does this first term become? When I shrink delta z, it doesn't depend on r, delta r, so it doesn't matter what r does. What matters is what z does. Partial derivative. Z direction of PGZ. If I shrink delta r and delta z, that does nothing to r. R doesn't shrink, just delta r. So this is minus 1 over r. And the rest of this is partial derivative, whoops, with respect to r of phi rz times r. Rho g has nothing to do with delta r, delta z is equal to 0. This part is thanks to curving coordinate system. I gotta account for how far I am from the center. Okay. Difference with x, y, z thanks to curving system. Okay. If I'm sending the same flux in r direction from my center of the wellbore, right? As my area changes, my flux phi per area diminishes the further I am away. And that's basically accounting for it, that r. Yes? So my equation is pretty similar to the Cartesian coordinate system except for this r action that has to account for the curving. Have we survived this? We are. Okay. So this is our general equation, and we are going to solve it next time. Okay. Now, I will be away on Friday, so I will record the video continuation of this and post the video for you, okay, instead of the class on Friday. Unless you would prefer Min to come here and talk instead of me. What's your preference, video or in some time?